Hi everyone, thanks so much for joining me for another LeetCode walkthrough. Today we'll be talking about problem number 23, merge k-sorted lists. As we discussed last time, one of the most important things while solving one of these algorithmic problems is being able to understand the input and the output correctly. Lucky for us, in this case, the input and output are pretty straightforward. So our input for this question actually has k-sorted lists. The problem that we are solving actually has linked lists. So I'm just going to mention that as well. So we have k-sorted linked lists. An example would look something like maybe one of my linked lists is 1, 2, 3. One of them is 1, 3, 5, 7. One of them is 3, 5, 7. So the point that I'm trying to make here is that numbers can be duplicated, and these are assumptions that you should probably clear with the interviewer as well. So the things that I'm trying to see here are, one, that numbers can be repeated. All of the lists can be of different lengths, like this is of length 3, this is of length 5, this is again of length 3. And then the number of lists is k. So in this case, k is equal to 3. And the total number of elements is n. So in this case, it's 3 plus 5 plus 3, 11. So our n is actually equal to 11. Now the output that's expected is a sorted merge list. So what that means is, if I had to merge all of these lists in a sorted manner, the way that I would go about it is find out what the smallest element in each of these lists is. So say currently it's 1, and here it's 3. So I'd pick up the smallest one. So it could be either of the first or the second list, but I'm just going to go with the first. So 1, and then the pointer for this list is going to move here, and then from 2, 1, and 3, the smallest is 1. So I'm going to choose 1, and then the smallest pointer will move here. Between 2, 3, and 3, the smallest is 2. So the head pointer is going to move here. Now between 3, 3, and 3, the smallest is 3. So I'm going to use this. Now this list is done. I don't have to think about it anymore. Between this and this, let's just take the first one again. So 3, and then 3 and 5. 3 is smaller, so we'll have another 3, and then this goes done. The pointer moves here between 5 and 5. Let's take this one. The pointer moves here between 7 and 5. It's 5. We take 5, and then we put in both the 7s. So as you can see, we can go step by step, and it's a very easy way to solve the problem. You go step by step over all of the nodes, starting with the smallest node in each list. And that is the advantage that we have, that the input lists that we have are sorted. We can just keep picking the smallest number at all times from each of the lists, and then writing the code also in the same way will be very easy. So one of the things that we need to do is analyze the time and space complexity. The space complexity in this case is very easy because we're just building a new list. So, and since the total number of elements is n, we'll be taking O of n space for making the new linked list. What will the time complexity look like? So we have n number of elements, and we have k lists, and for every element we are comparing it with at least k minus 1 other elements. So we can say that the time complexity is going to be in the range of O of n times k, which is, I wouldn't say it's polynomial, but even because most of these cases, either k will be much larger than n, or n will be much smaller than k, something like that. And depends on the interviewer's mood, to be honest. Are you asking about such questions? But even from n times k, is there a way that you can reduce the time complexity any further? The way that I like to solve these problems is I have like a list of complexities in my mind about what is larger and what is smaller. So for example, exponential complexity is always going to be greater than polynomial complexity, is going to be greater than linear complexity, is going to be greater than logarithmic. So if in this case we have n times k, the smaller than this is going to be n log k, or it's going to be k log n. Even smaller than that can be log n log k. But to be very honest, in my experience, I've never seen a complexity like this, or it's very rare. So maybe I'm not going to try thinking about this one to solve this problem. Between n log k and k log n, what is it that can be used? So again, when I think about log complexity, what are the data structures or algorithms that I know I can use which might end up giving me a log complexity. So in things like this, I think about maybe I can use trees, maybe I can use heaps. And in this case, since we are using comparison and we have some sort of an order that we're supposed to maintain, with practice you'll develop an intuition that you can usually solve such problems by using heaps. And so I'm going to try and see if I can use heaps. Another tip here is that whenever you see a problem, like I said, first I've already mentioned the order. And then if there are questions about, find the minimum K, or find the top K members, or find the last K members, these questions can also usually be solved by heaps, because as I was talking about in my article from yesterday about heaps, heaps are actually really good to determine priorities. Heaps are a special kind of a priority queue in which you can assign the priority to every single element in the heap. So basically these questions can also be easily solved using the heaps. Now coming back to the question that we're trying to solve using the order. Now again, my mind makes me think, okay, I might be able to use a heap. Can I use a min heap or can I use a max heap? What is it that might give me a better time complexity and might be more efficient in solving the problem that I'm trying to solve? So the only difference between a min heap and max heap is, say I have three numbers 1, 2 and 3. My min heap will look something like this, where the parent element is smaller than both the children element, and then my max heap is going to look something like this, in which my parent element is larger than both my child elements. So in this case, since I'm trying to use the smallest element and then I want to add it to my output linked list, that means I'm trying to pop the smallest element. Now it will be much easier for me to use a min heap then in this case, since I'm popping the top element at every time and then I can directly insert it to my output linked list. So now I have decided that I'm going to use a min heap, and then that's going to reduce my time complexity. And now I have to understand how is it that I can implement this in by using a min heap. So let's take a small example again to illustrate how we might be able to use it. So say I have a linked list 1, 2 and 3, and I have another linked list which is 2 and 4. So how we can start making this heap is that maybe I can take the smallest element values, same way, same thing that we did in the first experiment, and then put those in a heap. So my current heap should look like 1 and 2, but then I also want to keep track of where I am in the list. So I'm just going to put the value of the node, but also in the tuple I'm going to keep the linked list, so 1, 2 and 3, and then in this case 2 and 4. Now I also at all times have a track of my output linked list, so I'm going to pop the element and then I'm going to add it to my list, and then I'm going to check, does my list have a next element or not. It does have a next element, so I'm going to see this is what my heap looks like at the next step, 2 and then 2 comma 4. Does this still form a valid heap? It does, right? So I'm just going to keep it as it is, and then I'm going to pop it again. So my output now looks like 1 and then 2, and what does my heap look like? So once I've added 2, now I have to move 2 to the next element, so my value will at the top will become 3, and my list will look something like this, and then my value here is still at 2, and then my heap looks something like this. Now is this a valid max heap? No, this is not a valid max heap, so I have to make sure that I'm heapifying it at every single instant so that my heap is always a valid min heap. So maybe 2 can go on the top, so 2 goes on the top, so 2 comma 4, and then 3 comes here, so 3, and then that's just the null pointer. So now I can remove this, so my list will look something like 1, 2, 2, and then 4 is going to come here, so my heap looks something like this, so 4 and then 3. Is this a valid one? Nope. So I'm going to move 3, and now this is what my heap looks like, 4 comma star. So I'm able to pop 3, so my final list looks something like this, 2, 2, 3, and then 4 is going to be the only member left, and then 4, as you can see, this is a very valid answer, and in this way we have been able to use a heap to solve the same problem. Did we solve the problem of the time complexity? Let's check. So how does the popping work? So in this case I was showing it step by step, that the popping happens and then the heapify happens. In normal circumstances, the peeking at the element on the top takes only O of one time, but then popping and then the entire heapify operations, say there are, since we're already using k and n, I'm going to use L. Say there are L number of elements in a heap, then the popping operation is going to take O of log L time. In this case, how many number of elements do we have in the list at in the heap at each times? It's actually equal to the number of lists, because all of these elements are first elements of the lists. So this is going to be k elements in the list, so we can say that the popping is O of log k times. But how many times does this popping happen? We have total number of n elements, so the popping is going to happen n times log k, which is going to be our time complexity. So we have managed to reduce our time complexity from O of n times k to O of n times n log k, and then the space complexity actually remains the same, because we are still making a separate list which is n elements long, and the space complexity of the linked list will then be O of n. In some cases, the interviewers don't regard the space complexity of the output as valid space. So in this case, it will just be O of one space. In this case, still we might be using some memory in the heap, but for all cases, O of n should be a valid answer to this question. I hope I have been able to explain properly what was the input and the output, and one of the brute force ways, which is not as bad to solve this problem, but then just using an effective data structure such as heaps, that we can make this problem even more efficient.